All right, sorry, the birthdays fell on a bad day. I don't know what to tell you, but I'm already running out of time. Good morning. It's nice to see all of you. We are at the beginning of a new unit, so please have your spiral out, your slides out. Those of y'all at home, these are the what is this called? Reaction rate and mechanism slides. By the way, all of the lecture slides can now be found on YouTube on the videos for those of y'all that have gone and noticed. Not that it matters for y'all, but for those of y'all at home, there's a link below this video with the notes. All right, so Kinetics looks at a idea about chemical reactions that makes sense, that might actually feel weird that we haven't talked about before, which is, okay, well, what's the speed at which a reaction takes place? You can study the kinetics of any reaction, but what makes the products be created faster? What makes them be created slower? And in this unit, we'll be looking at different things that affect the rate of a reaction. So, kinetics is the study of the rate at which reactants are converted into products. Some reactions are faster than others. Some are slower than others. You've experienced that in our labs before. Some things happen quickly, while some don't. There's many things that can affect the rate of the reaction. The one that we're going to focus on today is what's called a mechanism. And a mechanism is actually, it's a pretty cool deal because instead of just looking at a normal reaction where it's, okay, well, these reactants create these products, it looks at some of the intermediate steps that actually happen while the conversion takes place that you're not used to seeing. You can switch. I did. Okay, so a couple basic ideas on the way just to look at change over time, which of course is what kinetics is using some of these equations. Now, a couple things I want to point out that's going to be true now and for a lot of future units. The triangle is a delta. That should not be new to your educational brain. But it means change over whatever. So it could be delta enthalpy, a change in enthalpy, delta T, a change in temperature. However, anytime we run into that delta sign, it's always going to assume final minus the initial. That's what the F minus I there means. I don't want to have to always say that when we run into change in something. It should just be automatic in your brain that if you're measuring the change in something, there's going to be a start value and an end value to show you the change. And to find the actual change, it's always the final minus the initial to find the change. Another thing that I don't think is new to you is what it means when a compound shows up in brackets. So if I give you that, for example, what is that going to tell you about hydroxide? What did you say? It's concentration. All right. What's another way to say concentration? Molarity. Those are the two same things. There's a student last class that I asked that she said moles. All right, that's what I'm worried about, is that y'all think concentration is the same thing as moles. It's not. All right, concentration is the same thing as molarity, and a component of molarity is moles. But just by having that one little misinformation in your brain can send you down a bad road when you're answering questions. So you want to have these things clear cut in your brain. If you look at those two equations, both of them, you can find the kinetics of a reaction by focusing on the reactants or the products. You can look at how quickly the reactants disappear, or you can look at how quickly the products form. So you'll see that those two equations there both put the change in the concentration of either of them over the change in time. But who can pinpoint the difference between those two besides reactants and products? There's a negative sign associated with the reactants. It's small, all right? I mean, if you have the slides printed out, you can see it. Up here, it's probably smaller. It's really important to point out that the reactants are negative there, and here's why. This is to equal the rate of the reaction. Well, you cannot have a negative rate, all right? The rate must be a positive number. This takes into account that the reactants are always going down, all right? Because as the reactants turn into products, you're going to have less reactants. So by making that reactant number a negative and assuming that the reactants themselves are going to be negative because they're going down, it ensures that you always have a positive rate. Now, even if you miss some part of my explanation there, then just memorize that if it's the reactants that are going into this kind of equation, that it's going to have that negative symbol there to ensure a positive rate. Now, before we get into our main focus of today, which is writing a rate law, I want to show you how you could have already kind of started figuring out the rate at which things are created just by looking at a balanced equation. All right. So here we've got 2 dinitrogen pentaoxides decomposing into 4 nitrogen dioxides and 1 mole of oxygen. What I see there when considering kinetics is a rate at which the products are made. For example, if I compare the one reactant to the first product, do you think that the NO2 is being made slower or faster than the reactant is decomposing?
Faster.
It's being made faster because every time 2 moles decomposes, 4 moles of NO2 is made. That means that it's not only is it happening faster, it's happening twice as fast. All right? So if that's true, and I again wanted to compare the rate at which the reactant is decomposing to the other product, how would you describe the rate? It is decomposing, it's that product is being created, the oxygen is being created half as fast as the reactant is decomposing. Do you see how I'm doing that? All right, so it's just looking at the coefficients like you have before, but in a different kinetic way. If I wanted to apply the equation from the previous slide to this idea, well, here's what you could do. You could say, all right, well, if I have the rate of, let's use my reactant as the focus, my N2O5, the concentration of N2O5, over the change in time, of course. Do you see how that kind of connects to the previous slide? Kind of the way it'd be written, but now I've actually put the reactant in there. All right. If I wanted to set that equal to the change of the NO2 concentration over the change in time, well, written like that, they're not equal. This is saying that their coefficients are the same, but they're not. What I know is that this guy's coefficient is a 2, right? Do you agree that N2O5's coefficient is a 2? You with me?
Yes.
If I wanted to make them equal to each other, they're not equal. I wanted to make them equal to each other. All right? What number would that 4 need to be multiplied by? And when I say that 4, I'm talking about the coefficient of the NO2. What would make this true? 0.5. And now this makes mathematical sense. If I set them equal to each other, I would have to say, well, for every one of these, all right, it's creating only at the rate of half there. So this number, in other words, is making the sentence true, the equality true. Okay, well, what if instead I was wanting to set him equal to the other product? The other product is O2. All right, so let's do the change in O2 over the change in time. So now I'm setting my reactant equal to the other product. See if you can come up in your head, we'll draw a card, what coefficient would make those be equal? And again, just think about it in these terms. No matter what, we want it to equal the reactant. You already know what that coefficient is. Let's go to cluster 3, seat 3. Diego, can you tell me, I'm totally serious, can you tell me the coefficient that would make this true? 2. He says 2. Do you agree?
Yes.
I agree. Because again, look at what he did. He said, okay, well, I want it to equal 2. The whole point is to equal N2O5, and his coefficient is 2. All right, the O2 is starting with what coefficient? 1. 1 if you look at the balanced equation. So what makes it true? All right. It's an abstract way of thinking when you just look at how these equal to each other. But if you understand how to get there, it should make it simpler. Questions? There was like 7 at this point last period, so there's more of you. Do you have any questions? Just comment below. I won't answer.
That's my job. I know.
All right, so here's another way to look at this coefficient idea before we get into the real stuff today. Anyway, now what you'll notice is there's a hypothetical reaction there, and what it does is the coefficients are missing. Not all of them, though. One of them is given to us. But then it gives us the rate of change of all of the parts. So what we have then is A plus B yielding C plus D. Which of the items, entities, does it give us the coefficient of? A. It says, hey, A is 2. And based on that, we can figure out all the other coefficients by looking at the comparative rates. For example, I want you to look at rate A compared to rate B. It's 0.05 compared to 0.15. Now, we need to be pushing towards the time where you can do logical questions without a calculator. The multiple choice, you don't get a calculator on the AP. For the FRQs, you do. You shouldn't need a calculator to rationalize this at this stage in your educational life. How much larger is B's rate than A's? It's 3 times larger. All right? Therefore, if it's 3 times larger, 2 times 3 is 6. All right?
Wait.
Okay.
Why don't we get a calculator?
You're not allowed a calculator on just the multiple choice questions on the AP.
But are we going to do like Stochastic?
There, but they set it up as the deal where all of these questions can be answered without a calculator.
But I don't want
It's like number sense.
Yeah. So I'm going to make up a number. So let's say that if, based on this list, if it said, okay, well, this guy is 6. All right, his time is 6, and this guy's time is 18. All right, how much larger is that number than that number? I tried to pick an easy one. I'm sorry. It's 3.
Just multiply by 3.
Hold on. Let's say that this guy was 1 and this guy was 3. How much larger is him than him?
3.
No, time. How many times larger? 3 times. Therefore, we're okay. Okay. Therefore, this number is 3 times larger than that number. Here, watch the next one carefully. Look at B's rate. You see how B is 0.15?
Yeah.
Now look at C's rate. Do you see how C is 0.075?
Yeah.
Can y'all see the comparison there? Is it twice as much? Is it 3 times less? What is it?
2 times less.
It's half as much because 0.075 is half of 0.15. So if B is 6 and C is half of 6, I bet you were. That was a funny joke. Okay, it would be 3. Now you can compare them to each other in any way. It'll give you the same answers. Let me do the last one more, and then we'll look. All right. So if, for example, let's compare A to D. Compare A to D. 0.05 compared to 0.025, you would say that D is half as much as A. Half as much as A would be 1. Therefore, we have a 2 to 6 to 3 to 1.
Wait,
why are you comparing?
wait, pull up.
Because you can compare any of them. That's what I'm saying. You can pick any 2 and compare them numerically. Here, let's do C to D.
Okay.
Watch, we'll get the same answer. Look at C. C is 0.075. D is 0.025. 0.25 is 1/3 of 0.075. And 1 is 1/3 of 3. They'll all connect mathematically. Amara.
So why is the polarity
Because it's being divided by time. It's putting molarity per time because that right there is concentration molarity over time. Yeah, the T stands for time. So that's the whole point of the kinetic is it has that time component.
Is that what the S stands for?
Seconds, yes. S is seconds.
So what, liters per second?
That's yeah. Well, this is moles per liter second is how it's said. You can change. All right, y'all. So the whole point of this is for us to learn how to write a rate law, and that's what a rate law looks like. You're going to need the slide in front of you while I explain this. So let's just talk about what those components are. First off, the rate is going to be the speed. All right, that's what we're trying to find is the rate. However, using mechanisms, which is what we're doing today, we can't find K. You have to have K to do this. So we won't be actually finding rates today, but mechanisms are an important part of chemistry. So we won't have K today. Even though it's your birthday, no cake today. Okay. There are two items that you're given concentrations of. Those will be the reactants always. All right? So you don't have a reaction to compare it to here, so we just got some made up stuff. But the nitrogen monoxide and the chlorine would be the reactants of a reaction because that's what's been put into those brackets. Do you see the M and the N? Those are called orders.
Those exponents?
All right, they are exponents. All right, those are called orders, and we're going to go over what that is in a moment. But in a nutshell, the order of the reactant, it's going to be a number, it's going to be a value. But the higher it is, the more magnitude it has, then the more important that reactant is in determining the rate. For example, if the M was a 2 and the N was a 3, that would tell me that the Cl2, the one with the 3, plays a bigger role in deciding the speed of the reaction. That's a big deal because if I was mixing NO and Cl2 and I was like, oh my god, I need this to happen fast, which one should I add more of? Well, whichever of the two items has the higher order is the one that more quickly affects the kinetics. So that's the one. I mean, you could change both of them and it would make it go faster or whatever, but the higher the order, the more important that reactant is for the kinetics. Now, we're going to be going over this through examples. It's not like you have to, oh, well, I got to memorize. All right, give yourself time. Now, while the individual reactants have their own order, which will be that M and the N, and those are just made up letters that they're different to show you that the numbers can be different. They can be the same too. But while the reactants have their own order, the entire reaction has its own order, and it shows you how to find it down here. What do you do with those exponents to find the order of the entire reaction? Just add them up. So in my example, it was a 2 and a 3. What would the order of that reaction have been? 5. 2 for one reactant order, 3 for one reactant order, whole reaction 5.
And the whole reaction is still the higher number wins?
No, this isn't like a limiting reactant deal. Both of them can be...
Like, it's for the whole thing, like it's measured the same way, like order of importance.
Right, but at that point you would be needing to compare reactions together. We won't be doing that.
Where
So,
would y'all get 5 from?
my theoretical made up numbers of 2 and 3.
If they were the same, how would you rate like importance?
They would be equally important. If you wanted to increase the rate, then just add more of one of them. Or more of both of them, and it would both affect, but it wouldn't matter which you picked. Okay, so what we're about to look at are what are called mechanisms, and it's the meat of the day because I want you to know how to analyze a mechanism. Again, I already explained it once, but this is where you take a reaction that you're used to seeing for a whole year of chemistry already, and we break it down into sub-steps that you didn't even know exist. And looking at the rate of those sub-steps is a way to determine the rate of the entire reaction. You can switch. All right, so there's the mechanism. I really hope that you have your printout of your notes, but I've got it written up here as well. Whoa, we almost lost a thing there. Okay. Now, I don't like that this problem gives you the reaction because most commonly in AP, you're going to be given just the mechanism and you're going to have to write your own reaction for it. So the answer is already there, kind of. But whatever. I'll show you how they get that reaction. A few things you need to know. First off, all of these reactions are going to have both what are called intermediates and catalysts. They're already defined in your notes, so you already have them written. But the intermediates are going to be items that somewhere in the mechanism are created, but then they're also taken away before they get into the actual reaction. So an intermediate is a part of the mechanism, but not a part of the final reaction. The other thing that you'll run into are catalysts, which I know is not a new word for you. I should be over here. But the catalysts are also items that will show up in the mechanism and not at the very end, or not in the final reaction. But, of course, catalysts are those items that are not used up during the reaction. Those are usually just there to speed up the reaction.
Did you say that your grade that you put in our grade book just to put in as an intermediate?
Okay. Anyhow, so let's take a look here. All right, so we've got this mechanism that's happening in 3 steps. This is all the same reaction. These are just the 3 steps that take place. What we need to figure out is what is the actual reaction. Here's how it works. The rules are written up there also. Anytime an entity appears both as a reactant anywhere in the mechanism and as a product, they will cancel each other out, but they have to be exactly the same. Listen again. Anytime you can look, and the whole thing is the mechanism. These are just the different steps of it. Anytime a reactant of the mechanism matches a product of the mechanism, you will cancel them out. So let's take a look at how that'll look up here. Hey, you see the HOI?
Boy.
Is he a product or a reactant?
Product.
He's a product. Do you see an HOI reactant anywhere?
Yeah.
Hey.
What? It's a sheet.
You get to cancel them out because you found a reactant and a product that matched each other.
Wait, so they're gonna, if you had this, they would give you all 3 of that?
Yes.
Oh,
Yeah, they
okay.
give you the whole mechanism. Yeah, you're not going to have to write mechanisms from reactions. They will give you the mechanism.
Nice.
All right? So, do you see any others? Now, the other one is trickier, but it's there. See if you can see the other item that needs to be crossed out.
The 2OH and 2H.
The 2 OHs. These are 2 OH minuses, which is the exact same thing as 2 OH minuses.
Oh my
Wait,
goodness.
so it's not just
Okay, so you can't,
in
you
the
can't
other
cross
line?
out those eyes right
Anywhere in the mechanism. Anywhere, not in the same line. Anywhere, no, I'm going to answer your question. Anywhere in the mechanism. All right? Now, Annalise's question was, well, isn't I minus and I minus equal to I2? No, because I2 is your diatomic molecule, while your I minus is up here is just the ion. This is exactly 2 ions. These are 2 OH minuses, which are the exact same thing.
Me, right?
Yes, totally.
So like the only reason why we can't do it too is just basically also because like that's a subscript, basically.
Exactly. It makes it different because I minus is different than I2. Absolutely.
Yes, right?
Subscripts, but are you referring to?
Yeah, for you to cross it out, you need to be a coefficient.
Right. Yeah, a coefficient, because realize that 2 OH minuses is really OH minus plus OH minus plus. That's what it really is. We just don't write it like that.
So then, what about that?
What about the?
Okay, well, what about the 2 I minuses, though? Why can we not cross them out?
They're reactants.
Because they're both reactants. It's got to be a reactant somewhere matching a product somewhere. These do match each other, but they're both on the reactant side of a mechanism step.
Oh,
What about the?
like,
Anywhere, the whole thing counts, but you can't do a reactant with a
it
reactant.
has to match left and right.
What
Left and right.
The H2O2 and the 2H.
Okay, so this is water and hydrogen peroxide. Those
So that's what I
are.
was gonna ask.
And then the
If that was a
2H.
4 on the H, would you be able to cross it out? Like look on the top, the left
Like, if that was an H4O2.
No, because that's a totally different compound. I mean, because like realize here, like water compared to hydrogen peroxide, you can swallow one of those. All right. So just because you're counting up elements and they look similar, guys, it's got to be exactly the same.
Ah.
So if there's like H2O and H2O, you said?
Yeah,
they're not-
absolutely. As long as they're on different sides.
So the arrow.
Okay, so
What was the school and like facts?
I haven't gotten there yet.
Yeah, Robin.
Yeah, ramen. Okay.
Who's that?
So from this information, we can write the equation because everything we didn't cancel out is the equation. All right. Oh, before we write the equation. Okay. So intermediates and catalysts. Everything. Focus. Everything you cross out is either an intermediate or a catalyst, and it's super simple to figure out what's what. Catalysts can only be found at the end of the last step. It already says it on there. Catalysts can only be found as the product of the last step of the mechanism. You see how that's the product of the last step of the mechanism? Did we cross him out? Then there are no catalysts in this equation. It can only live there. So here's another way to think about it. All reactions have intermediates. Not all reactions have catalysts. All reactions have intermediates. Not all reactions have catalysts. Because what are these other ones? Those are intermediates. So listen again, let me say it one more time. Everything you cross out is either an intermediate or a catalyst. But it's only a catalyst if the item crossed out is a product of the last step of the reaction. Now some of y'all are trying to write down what I'm saying. It's written, you've got it. It's up there.
Could it be, if there was a plus sign, is it both of the products?
Yeah, there's two products.
Can it be both of the products are catalysts? Or is
No, well, you're always going to have one thing over here that's not crossed out, but there can be multiple items over here.
So to
Wait,
ask
all-
Well, that's not even true. No, that's not true. You won't always have something over there. That's not correct. That's not true.
No, so all of them would be a catalyst?
Yes, right, but only focusing here. Yes, but they would all be catalysts at that point.
So basically, so if catalyst is so if last thing is crossed out, it equals catalyst.
Absolutely, that's it. That's it.
And if there's more than one, then like.
Then you have more than one catalyst.
Okay, so
Robin,
Can you repeat that, like, all reactions have intermediates?
all reactions have intermediates. Not all reactions have catalysts. All right, guys, let's keep going. Well, let's see where I am. I don't want to go beyond the slide.
wait, so there's two catalysts in this.
There are two catalysts in this one. Now, you can switch slide.
Wait, how are there two
What are the
catalysts?
catalysts?
No, there's no. Sorry, there's. I walked away from the board answer. There's two intermediates. All right, really three intermediates, and no catalyst.
What about the one
To
on
be
the
like the
left?
bottom.
We're products only, guys. Products only.
Bottom right.
And here's why. Here you'll see in the thing we're about to draw that why it's products only is because realize that the product over here is the same thing as the reactant over there. You'd be double counting it.
And why is the catalyst in the actual final reaction if it's not allowed there? Because you're not crossing it out. Like, no, but like, the catalyst.
Okay, so let's look at the final reaction. That's what we haven't done yet. I tried to do it and I stopped. In order to write the final reaction, we just bring down everything that's not crossed out. All right? So, H2O2 is not crossed out. I've got two I minuses that are not crossed out. I've got two H pluses that are not crossed out. On the product side, I have one I2 that is not crossed out and two waters not crossed out. Now, someone asked, why is the catalyst in the final? Remember, this equation has no catalyst. Catalysts are only catalysts if they're crossed out. And you'll see that matches what's up here. That's why realize that it will usually give you the mechanism, but not the reaction. You find the reaction by doing this process.
What's that called? The final.
This is just the chemical reaction. This is what you're This is what you're used to seeing.
Okay, so
This is the chemical reaction.
They said find that, or we have to find.
If it said find the overall reaction, you would do this exact step where you cross out and then bring down what you didn't cross out.
on the 2H2O, if that was crossed out, that'd be a catalyst?
Right.
Okay.
That's the only place a catalyst could exist. Is the last step is the product of the last step. Yes, yeah, absolutely. We just haven't gotten there yet. Yeah, you said does the order matter, right? Okay, yeah. We're inching. Oh wait, hold on. Did you do it already? Yeah. Okay. No. I haven't done that yet. Okay. No. Freeze. You're good. So the energy profile is another cool thing that we can do to represent the steps of the mechanism. Just yelled at those people at home.
And that's baseball.
Okay, here we go. An energy profile is a pictorial way of showing the rate of the different steps. I want you to look back at the mechanism. And as was asked a moment ago, do you see the words that I've ignored so far?
Fast.
Some of the steps are faster than others. Here's what an energy profile would look like for this reaction. Can anybody explain to me why you think my first hump is the largest? Just yell it.
Potential energy. I don't know.
Because that's the slow step. If you look back over, there, you'll notice how many steps are there in the mechanism?
3.
So 3 humps. Which one's the slow step?
The biggest
The
one.
first one.
Takes the
All right? So the slow step is the step that is going to determine pretty much all the kinetics of the reaction. For example, if you were going to go on a race, and your race was to start right here on the path and end right here, and I was like, hey, I'll change one part of the path for you. Which part would you want me to change? Yeah, stupid guy here, right? Because this is the one that is determining how fast you run the race way more than the other 2 steps. So what we call him is the rate determining step. You don't actually put that there, but if you just, you can like draw an arrow or something. But RDS stands for the rate determining step. All right, it's on your slide. Because the slow step is the one that will determine the rate of the reaction.
So, does the size of the hump have anything to do with?
At this, we can draw a prettier graph. We're just not yet. All right. What I need is for the slow step to be the big hump and the other ones to not be.
It determines the rate of the reaction.
The slow step determines the RDS.
Okay.
All right. Now, another thing that we can look at here, though, is where the intermediates exist. Because we know that intermediates and catalysts exist at the end of steps, right? So, for example, can anybody tell me, are there any intermediates or catalysts right there?
No. Yes.
What? Oh, yeah. Look, at the end of the slow step, what's there? HOI and OH minus. So the intermediates of those guys, HOI and OH minus, they both existed right there. Yeah, we crossed them out, so they're not going to be a part of the reaction. But while we're showing the mechanism, that's where they were, at the end of the slow step. Hey, but I asked that question in a stupid way. Here, let me ask the question. Here's what I asked. I said, what intermediates or catalysts exist there? How should I have asked it?
What intermediates?
Why should I have only asked for intermediates? Because it's impossible for a catalyst to exist there, because what's the only place a catalyst could exist? At the very end. So get your head wrapped around some of the subtleties there. Okay, so let me ask it the correct way now. Are there any intermediates there? HO minus or OH minus. I'm not dyslexic, you are.
What happened to I squared? Oh, it didn't get canceled out.
Didn't get canceled out. Not an intermediate. All right. Hey, are there any catalysts there?
Nope.
Nothing.
Did we just do that prize?
No, you don't put it. Just
Oh, okay.
y'all. I know. Y'all. I get it. Y'all are literally think everything means something.
Okay, so for some reason I'm kind of confused. It's not really actually clarification. So you only write the intermediates if they're a product.
Exactly. Yeah. So guys, when you're identifying, understand this. You're going to be crossing out reactants and products, but when identifying the intermediates and the catalyst, products only.
Wait, so you want us to create this equation, balance it, do all that, cross them out, make this graph?
All from me giving you the entire mechanism, though. You don't have to come up with the mechanism.
Oh.
So it's like just like okay, go ahead. Can the catalyst be slow or are they always gonna be fast?
No, the slow step can be the last step.
So is that how it's gonna look on Schoology?
Yes, that's how it's going to look on Schoology. You'll be given the mechanism and determining stuff from that.
Whatever we just did with you on Schoology.
I'm sorry. Yes.
Okay. Yeah.
All right, back here. Guys, I'm not going to finish. I'm going to be teaching to this dang screen by myself in here. Okay. Okay, so then what about writing the rate? So let's focus on how to actually write the rate law, because that's really what we want to be able to do. So here's what the rate law looks like. All right, thank you. To write the rate law, it's going to be rate equals K. Hey, remember, we are not finding K today. I already mentioned that earlier. All right? And then, hey, remember, we looked at this in an earlier slide. It's going to put the reactants in brackets for concentration and raise to the power. Hey, what was that power that we raise it to called?
Order.
The order is the vocab word. Now look here. Quit writing for a second. The rate law will only look at the reactants of the slow step because that's the only thing that decides the kinetics of the reaction. It's only that big hump that determines the rate, because once you focus on him, the rest of it is so much faster. So listen again. The only items that will ever go in the rate law are the reactants of the slow step. Hang on, hold on to your question. So find the slow step over there. What's the first reactant?
H2O2.
The order that you're going to put, the exponent, will simply be equal to his coefficient in that step. What is H2O2's coefficient right there?
1.
It's 1. Now we don't show ones, so you can't write it. But there's a 1 there, all right? Like I want to write it so that you can see the numbers for our first problem here, but then you look back on your notes, you're like, oh, I'm supposed to write a 1. Don't write 1s, all right? Hey, are there any other reactants on that slow step?
Yes.
Okay, what's the other one?
I minus.
What is it?
I minus.
All right. What is I minus's order?
1.
It's 1. He also doesn't have a coefficient. So there it is. That's the entire rate law for the problem. Almost. Question asked quickly.
You don't have to put like a plus sign or anything in between.
No, because they're multiplying. Because once we actually put numbers in there, it's him times him times him with them raised to their powers. There's just not a power in this problem.
Will there ever be two slow?
No. Only one slow step.
Can you finish what you were saying? The only items that will ever go to the rate law?
Are the reactants of the slow step. Now, there's one more item, unfortunately, that we have to input here. Listen to these words. Now, it's written there. It's the bottom thing. I'm reading off the slide. If there are any reactants in that overall reaction that are not in the slow step, then they need to be included in the rate law. Listen again. If there's any reactants in the overall reaction, look at the overall reaction at the very bottom, that are not in the slow step. Are there any? Yes. What is there?
I minus.
No, I minus is there. H plus. All right. It also is included to an order of 0.
What? And why is this again?
You must do this because the whole point of the rate law is for me to look at the overall reaction and figure out who is doing what. Here's what I see when I look at this now. I see that if I want the reaction to go faster, I can add either H2O2 or I minus. If I do that, it'll make it equally. They're equal to each other. One's not better than the other because they both have an order of 1. Do you agree?
Yes.
All right. But what happens if you add more H plus?
It won't do nothing.
Nothing. It doesn't change the speed of the reaction. So by looking at this, now I know that, okay, I want the reaction to go faster, add I minus. All right, and then you see the other lab person across the room adding H plus, you just laugh at them. Because that's not going to make it go faster because H plus has a power, an order of 0.
It's not slow.
I'm sorry?
You don't include the two?
No, here it doesn't. Because everything here is just, it's just the ion.
Would you include the two if it was in the slow?
Yes, yeah, you'll write it exactly as is.
It's not great.
So, hang on, let me finish, guys. So, we know the order of each reactant. The last thing is the order of the reaction. Does anyone remember how we find the order of the entire reaction? You add up the orders. What do you get if you add up those 3 orders?
2.
This is a second order reaction.
You're doing the second.
What?
You just add.
Wait, that's the rate.
1 plus 1. This is the rate law. That's the rate law. This is just the order of the reaction.
What does RDs mean?
RDS stands for rate determining step. It's the slow step. They're the same thing.
Sir,
Yes.
so why did you select for the I negative? Why didn't you put the 2 coefficients?
Well, so I'm going straight from the slow step.
Oh, okay.
It's coming, remember, it's coming from a step of the mechanism, not the overall reaction. All right, so again, hopefully you have this already written down from the slides. I don't have time to explain as I have, just watch. Watch me do another one, all right? Here's what I want you to be able to do on Schoology. I want you to look at a mechanism, all right? I want you to say, okay, I need the overall reaction. Here's what I see. I have a Huber and a Huber that matches reactant versus product. I also have two HOBRs, 1, 2. That is everything that matches when you compare reactants to products anywhere. Then I can say, sir, what are the intermediates? How many intermediates do you see?
2.
1. There is 1 intermediate. When looking at intermediates and catalysts, we are only looking at the products of each step. 1 intermediate. How many catalysts?
1.
Hey, there he is. There's your 1 catalyst.
Wait, what about
There's 4.
What about the one on the top?
Mechanism?
What one on what top?
The Hoover. Wouldn't it be 3?
There is no Hoover at the top.
The one where it says slow.
Yeah, HOBR.
He's an intermediate
Why?
because everything crossed out is either intermediate or catalyst.
So where'd you get 2?
I said 1. We have 1 intermediate and 1 catalyst. It's always only from the product side when looking at intermediates and catalysts. All right, what's the energy profile look like? Well, how many humps should there be? 4. It's a hump for every step. Watch how I do it. I would go 1, 2, 3, 4. Do you agree? The slow step is the 3rd part of the mechanism.
No, I don't understand.
You say that you don't care. Like there might be a different rate on the other step, but who cares? The slow step determines everything. All right, hang on, guys. Y'all hold on to it till the end. I'll answer all of your questions through the bell, but let me get this before the bell ends. All right, where do the intermediates live? Well, check it out. There was 1 intermediate at the end of the slow step, so that has an intermediate, and there was 1 catalyst at the very end of the last step. So that's where the intermediates and catalysts are. All right, it wants to know the rate law. All right, well, here we go. The rate equals K. Hey, where am I going to look for the rate law? The reactants of the slow step. Slow step, reactant 1 is HBr. Slow step, reactant 2 is O2. All right. They're both to their first order. All right, because there are no coefficients there. All right. I know. Yeah. What are you doing actually?
I thought.
No. Go away. All right. Hey, what's the order of the reaction?
2.
2. All right. Oh wait, did I write the reaction? Oh, I didn't write the reaction. Y'all should have yelled at me. All right. I skipped the part where we bring down all the stuff that we didn't cross out. Sorry.
We're good.
So what does the overall reaction look like? Well, look, how many HBRs are there?
4.
There's 4. There's 4 HBRs. All right, what other reactant do you see?
O2.
An O2. And that's producing, all right, look, there's 2 BR2s. All right, there is 2 waters. Now, the reason, like someone said, no, we're good. You need this because you need to make sure there's no 0 order reactants. Are there any 0 order reactants? No, not in this one, because every reactant in the overall reaction is a part of the slow step. So now there's nothing to raise to the power of 0 because the slow step didn't lead out a reactant.
The order's 2.
So
This is a second order. 1 plus 1 is second order.
why is there not a 4 on the HBR?
There's 1 in each.
Why is there not a 4 here?
Yeah.
Because the coefficients in the rate law only show up as exponents.
What? So then when we put the 4 in the exponent?
No, but this is the slow step that we're pinpointing.
Okay.
Now realize, guys, look, if this was HBr plus 2O2, it would still just be O2. in the brackets. Where does that 2 go? It would be, that's where it would go. And now it would be a third order. And if this was true, if that was true, who would you add more of to make the reaction go faster? The oxygen, because the higher the order, the more important it is for controlling the kinetics.
So to get the actual powers, the order, you have to look at the mechanism, not the final equation.
To find the overall order, you add up the exponents of the rate law.
I mean the order from those.
Yes, to find the orders in the rate law, you look at the slow step coefficients.
What is the bottom part for? What did you
This?
find?
This? Yeah, I brought down everything that I didn't cross out, which was 4 HBRs and O2, 2 BR2s, and 2 H2Os.
Where's that H from?
Which one?
There. Oh, on the hump, on the bottom hump, right there. On the back. Yeah, yes.
That's an I.
I.
I was showing that there's an intermediate located there, and there's a catalyst located there. Intermediate catalyst.
I feel like I missed the slow step. Like, how do you determine that that one's the slow step?
The slow step is just given to you. Look,
Oh,
that's the problem.
cool.
So we never have to find that?
No, they'll tell you.
Okay, good. You as a chemistry teacher, do you have to find that? Like, do
You can find the mechanism. We're not going to do that in this class.
Okay.
Bye-bye, everybody.